Okay, so guys, in order to introduce frame of reference and then later get into the mathematics, I'm going to show this video to you guys um, that was made in 1960. Even though it's an old video, it's still the best video out there that introduced reference frames, which is why I'm going to show it to you guys right now. We're not going to watch the whole video, but we will watch just a few minutes of it so you guys can get the point. Okay, so I'm going to share my screen. Today is third period. So go to third period class, click on the folder for today. There's a video titled Frame of Reference, or in other words, there's a link to a video titled Frame of Reference in 1960. Okay. And again, the purpose of this video here is to demonstrate that whenever you are describing motion, it's very important that you describe motion relative to a reference point, right? If something is moving, what is it moving relative to? You have to establish a frame of reference whenever you are mathematically describing motion. Okay. You know what? Let me go and share my sound just to be sure you guys can hear this.
We are used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now, I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up. which is a different direction here than it is on the other side of the Earth. And these two reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this Earth frame of reference and in other frames of reference moving in different ways relative to the Earth frame.
Okay, guys, I'm going to fast forward to the end of this video because the end of this video, this is the most important part here, because here is where they really show you guys how to convert mathematically between different frames of references, which is what we're going to be using for our assignment that I'm going to post today. We're going to be using these principles for the assignment I'm going to have in Schoology as soon as I'm done with this. No, guys, you don't have to take notes. This video is going to be posted on YouTube. But by the way, guys, if you guys are sending me a private message, I cannot see the message when I'm sharing my screen. Okay, so if I'm sharing my screen, just send a public message and I'll see it on my other computer. Okay, so just want to let you guys know that. Okay, the attendance form is now in the chat box. Okay, let me continue sharing the screen, and we're going to finish the end of this.
Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards? I'll try. If Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now, we are on a car here, a car which can move and which really is going to move in this direction, and we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is, the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. And I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind. Here's the cart, which was moving along in this direction with a velocity u. We were sitting on the cart at a table. Here I am over on this side, and Dr. Hume was on this side, and we were pushing this puck back and forth on the table. When I pushed it, it went in this direction with a velocity v, and when Dr. Hume pushed it, it went in this direction with the same velocity v, but this is the velocity relative to the cart. What about the velocity relative to an observer on the ground in the fixed frame? Well, if it was pushed in this direction, its velocity is u plus v. If it's in this direction, its velocity is u minus v.
Okay, so guys, that's the important point there, that basically what he's saying is whenever you are converting velocities between different frames of references, all you do is just combine both velocities. You either add or subtract depending on the direction that you're dealing with. So in other words, what he's saying is if someone's on a cart and they observe an object moving at a certain speed, this equation right here just shows you what the observer will notice of that same object if they are not on the cart, if they are in another frame of reference. So assuming that they are, in a frame of reference that is, attached to the Earth. In other words, they are at rest relative to the Earth. So I want to play this brief clip again because I thought this was the most important part of the video. Notice how whenever you are moving along with the cart, notice how the speed of the puck in this direction was the same speed of the puck as it was traveling in this direction. However, when you switch your frame of reference, in other words, you are no longer moving with the puck, but you're just, stationary on the ground, you observe that the speed will look different. So let me show you guys that now. Okay, so this is when you're moving with the car. Okay, but then we're going to change frame of reference. We're going to instead of moving with the cart, we are going to observe this from a coordinate system in which we're stationary relative to the Earth. Okay, here we go. So notice in this point of view, look at the speed of it moving in this direction. But notice how it appears to be going slower, moving in the opposite direction relative to that background there. And that's because we changed frames of references. Well, we changed our frame of reference. Okay. So with that said, let us get into some example problems or some example situations before we do our example problems. Okay, let me pull up the PowerPoint. Give me just a second. Okay, let me give you all some examples, or an example of how to convert between different reference frames mathematically. Okay, so guys, imagine here that we have a moving train, and this train is moving in this direction here. It's moving toward the east. Okay, so we have this moving train, and we have an observer standing outside the train. Okay, and this person right here, he's looking. Well, this person in green, he's looking at this train go by. And as this train goes by, there are two people on the train. There's someone in red and there's someone in blue. Now, guys, this person in green, as he watches this train goes by, from his perspective, he notices that this train is moving with a speed of 70 miles per hour. Again, that's his point of view. Okay, so just follow me. Follow what I'm saying here, guys. I'm just showing you guys how to convert between reference frames. Okay, so he's watching the train travel at 70 miles per hour from his perspective relative to the ground because he's on the ground. Oh, hold on. Sorry, guys. Let me. Okay. But let me ask you guys a question. Well, you know what? Before I ask the question, real briefly, let us go to the frame of reference that is inside the train and kind of figure out what's happening here. So, guys, inside the train here, this person here is holding a ball in his hands. So he has a ball in his hands. And so the person in red, he decides to throw the ball to the person in blue. And as he throws the ball, from the point of view of the people inside the train, okay, in other words, from his point of view and his point of view, they both see their ball traveling at 5 miles per hour relative to their perspective inside the train. Okay, so Someone tell me, if this guy right here sees this ball traveling at 5 miles per hour, from the point of view of the person in green, how fast is this ball moving? Does anybody know? Keep in mind, though, that the person in green, he's watching the train move, and he's also watching the ball move as well. It's not 70. Again, I'm going to say this again. From their point of view, they see the ball moving at 5 miles per hour. But from this person's point of view, notice he see the ball moving with the train. So from his perspective, how fast is the ball moving? Anyone else want to take a guess? No. The people inside the train see it moving at 5 miles per hour. Exactly, Braxton. So it's moving. The person in green sees the ball moving at 75 miles per hour. So this person right here, when he looks at that ball, he says, "Oh, that ball is moving at 75 miles per hour." Okay. And guys, think about why that is. Because again, he sees the train moving. From their point of view, they're just standing on the train, and so this person, from his perspective, if this ball is coming at him at 5 miles per hour, that means this person right here must see the ball moving at 75 miles per hour. Because remember, he's outside the train. Okay, and remember what they said in the video. Whenever you're converting between reference frames, all you do is just add or subtract your velocities depending on your direction. So we're just combining our velocities here. 70 plus 5 gives us 75. Now, guys, let us discuss another situation. Suppose, suppose that, after this person right here in red threw the ball, the person in blue caught the ball. Okay. So the person in blue, they caught the ball. And as soon as the person in blue caught the ball, he decided to throw the ball in the opposite direction toward the person in red. Okay. So he threw the ball at 5 miles per hour in that direction. Now, someone tell me, if the person in red notices the ball is coming at him at 5 miles per hour, now from this perspective, from the perspective of the person in green, how fast is the ball moving? Exactly, it's 65 miles per hour, because notice we threw the ball in the negative direction. So when we combine those velocities, so 70 minus 5 is equal to 65 miles per hour. Okay. So that just gives you guys an idea of how to convert between different reference frames. In other words, if someone sees something from this point of view, if you were to move to another point of view, you can figure out how fast you're going to observe an object moving from that point of view just by combining your velocities. All right, so I think for the most part, you guys all get that. Let me stop sharing my screen. And of course, I want to spend like the last 5 minutes or so just doing a few examples that will look like the examples that you could see in your homework. Okay. So give me just a second while I pull up this PDF file. Okay, so I'm going to read what's happening here, and then we're going to work on the first 3 together. Okay. So this says, shown below are 6 situations where people are walking or running along flat train cars. The people are walking or running at various speeds, either in the direction the train is traveling or in the opposite direction to the train's direction. The speed of the train and the speed of the speed of the train and the speed and direction of each person relative to the train are given in each figure. An observer is standing beside the train watching the train go by. So the question is, what is it that this outside observer noticed of the people on the train? So, crap. I'm sorry, I didn't mean to do that. Let me trying to hit this annotate key. Okay, so guys, let us pretend that we have someone here. You know, they're standing outside the train. They're standing outside the train and they're watching the train go by. So, so we have an observer in green here. Okay, so this person in green, they're looking at these various situations here, and so, before we begin working this out, let me just kind of explain to you guys what these numbers mean here. So guys, you see this velocity here, the velocity of the train at 24 meters per second. What this number right here is telling us, this number right here is telling us how fast the train is moving from the perspective of this person in green. So relative to their frame of reference, that train is moving at 24 meters per second. Okay, this number right here, 8 meters per second, guys, this number shows you how fast this person is moving relative to the floor of the train itself. So in other words, just looking at the floor of the train, this person is moving at 8 meters per second relative to someone, on the train, and they're seeing this person move from that particular perspective. Okay, so guys, the question is, someone tell me, what do you guys think here? If this person in green sees the train moving at 24 meters per second, and this person is moving at 8 meters per second relative to the floor of the train, someone tell me, from the perspective of the individual in green, how fast is this person moving from his perspective? Exactly. Thank you, Zoe. Thank you, Hannah. Thank you, Tyra. 16 meters per second. Exactly. And here's how you guys knew that. I'm telling you guys right now, whenever you guys are working these problems, it's very important that you guys get your sign correct. So in other words, guys, any object that is traveling toward the east, you want to call that direction positive. And any object that's traveling toward the west, you want to call that direction negative. So guys, if you combine positive 24 with negative 8, what you get is positive 16 meters per second. So that means this person on the train is moving at 16 meters per second, from the point of view of the observer in green. Okay, from their perspective. And again, they're moving toward the east because that's what the sign tells you. The sign tells you your direction of travel. Okay. So guys, let us look at situation B here. Okay, so this person in green here, they see the train moving at 30 meters per second in that direction toward the west. So again, from the point of view of the person in green, the train is moving at 30 meters per second. Now, guys, from the perspective of the floor of the train, this person is running at 10 meters per second relative to that train. Okay. So guys, the question is, how fast is this person moving relative to the person in green? From their perspective, how fast is he moving? Okay. Well, I'm going to tell you guys right now, remember what I said before. Any arrow that's pointed toward the left, or in other words, pointed toward the west, you want to call that velocity negative. And when it's pointed toward the right, you want to call that velocity positive. Okay. So guys, when we combine these velocities, what is the velocity of the person relative to the point of view of the person in green? Thank you, guys. It is negative 20 meters per second. Okay. Okay. So, guys, from the point of view of the person in green, this person is moving toward the west. That's what the negative means. The negative means they're moving toward the west. The positive means they're moving toward the east. Okay. Let's do one more, and then I'm going to let you guys go. Okay. So look at situation C. First thing we want to do, we want to label our velocities. Remember, if the arrow is pointed toward the east, we want to call that positive. And if the arrow is pointed toward the west, we want to call that negative. So can someone tell me, if this person right here sees the train moving at 20 meters per second toward the east, and the person on the train is moving at 4 meters per second relative to the floor of the train itself, someone tell me what is the speed of this person from the perspective of the person in green, from the someone who's just, he's standing on the earth and he's watching this train go by. Yes. In this case, it's positive 16 meters per second. Your direction matters here, as you guys will see when you guys complete the homework assignment. So this person is moving at 16 meters per second toward the east, because the positive direction, the positive sign indicates the eastward direction, and the negative sign indicates the westward direction. Any questions? Okay, guys, I'm going to go ahead and stop recording.